Hello students, in today's lecture we are going to learn about mechanical properties of fluids, NCERT section 9.2.2 to 9.2.3. We will also solve an example 9.3. This is disclaimer, learning objectives. By the end of this lecture you will able to understand how pressure varies with depth in fluids and derive the mathematical relationship between pressure, density, and height. Explain atmospheric pressure, gauge pressure, and their measurement using devices like mercury barometer and manometer. So, in today's lecture, we will cover first 9.2.2 variation of pressure with depth. After that, 9.2.3 atmospheric pressure and gauge pressure. And last, we will solve an example 9.3. So, now we are going to explore how fluid pressure changes when with vertical depth. This is a fundamental concept in understanding the behavior of fluids under the influence of gravity. So, variation of pressure. Let's start by discussing the variation of pressure. This concept is a crucial application of Pascal's law, which tells us that pressure applied to a confined fluid is transmitted undiminished throughout the fluid. Now, let's set up the physical scenario. So, consider a fluid at rest in a container. Look at figure. We see a vertical cylindrical column of fluid as shown in figure 9.3. So the figure 9.3 shows how gravity affects the pressure within the fluid. So in the figure 9.3, point 1 is located at a height h above point 2 and pressures at point 1 and 2 are P1 and P2 respectively. Now uh, let's see the mathematical derivation. So it's important to note that the fluid is at rest. This means that the resultant horizontal forces must be zero. Additionally, the vertical forces need to balance the weight of the fluid element. So here the cylindrical element of fluid with base area A and height h. As the fluid is at rest, the resultant horizontal forces should be zero and the resultant vertical forces should balance the weight of the element. Now, let's start by considering the forces acting vertically on a fluid column. So, for equilibrium, these forces must balance each other. So, first, forces acting vertically. So, the downward force at the top of the column represented by a P1A, pressure at top. This is the pressure at the top multiplied by area. Next, we have the upward force at the bottom of the column, pressure at bottom, represented by P2A. This is the pressure at the bottom multiplied by area. And downward is weight of the fluid, that is mg. So we arrive at the equilibrium condition. P2A is equal to P1A plus mg. Alright, and this equation shows how the pressure at the bottom is equal to the pressure at the top plus the weight of the fluid. We also have a downward force mg that is due to the weight of the fluid. Now uh, let's consider the mass density of the fluid, denoted by Greek letter rho. Mass density is the mass per unit volume of a substance. So the equation, mass is equal to density into volume, rho into volume, is equal to rho HA. Shows us how to calculate the mass of the fluid. Alright, here rho is the density, V is the volume, H is the height, and A is the area. Equilibrium condition. So equilibrium condition is given by the equation P2A is equal to P1A plus mg. Here P2 and P1 are pressures at different depths. A is the area and mg is the weight of the fluid. Alright. So rearranging the equation gives us P2 minus P1 into A is equal to mg, which is an important result from the equilibrium condition. So P2 minus P1 into A equal to mg. It tells us that the difference in pressure between 2 points in a fluid is due to the weight of the fluid between those points. Therefore, we can express pressure difference in terms of density, gravity, and height. So the equation P2A is equal to P1A plus rho GHA, because the mass of the fluid is rho HA. Simplifying the equation, we arrive at P2 minus P1 is equal to rho GH. Alright, so this is important equation. The pressure difference depends on three parameters. Alright, first, vertical distance h between the points first and second. Second, mass density of the fluid rho, and acceleration due to gravity g. So these are the points on which pressure is depend. Pressure depends on these points. Now, if point first is at the surface open to atmosphere, and P1 may be replaced by atmospheric pressure PA, and we replaced P2 by P, then equation 9.6, P2 minus P1 is equal to rho GH. Here rho represents the fluid's density, g is the acceleration due to gravity, and h is the vertical height between the 2 points. So using the equation, we can derive that the pressure at a certain depth P is equal to the atmospheric pressure plus rho GH. Thus, the pressure at a depth below the surface of a liquid open to the atmosphere is greater than the atmospheric pressure by an amount rho GH. This means that as you go deeper into a fluid, the pressure increases because of the weight of the fluid. So the excess pressure at a depth h, which is P minus PA, is known as gauge pressure at depth h. Now, Let's start by noting that the area of the cylinder does not appear in the expression for absolute pressure in the equation 9.7. So we have a 9.7 equation, that is P equal to Pa plus rho GH. In this equation, P is the absolute pressure, Pa is the atmospheric pressure, rho is the fluid density, and G is the acceleration due to gravity, and H is the height of the fluid column. Notice how the equation emphasizes the role of the fluid's height in determining pressure rather than the area or shape of the container. This means that whether the container is wide or narrow, the pressure at a given depth remains the same. As long as the height of the fluid is same, the liquid pressure at the same horizontal level. Let's see. So liquid pressure is uniform at all points at the same depth. Alright. This means that if you were to measure the pressure at different points along the same horizontal line in a fluid, alright, you would find it to be the same. Hydrostatic paradox. This principle states that the pressure at a given depth in a fluid depends only on the height of the liquid column, not on the shape or volume of the container. Now, let's consider three vessels labeled A, B, and C, each with a different shape. Alright, look at figure 9.4. Illustration of hydrostatic paradox. The vessels A, B, and C contain different amounts of liquid, all up to the same height. So, although they have the different shapes, they are filled with the liquid to the up to the same height. These vessels are connected at the bottom by a horizontal pipe. This connection allows the liquid to move between the vessels. When we fill the vessels with water, the level in each vessel becomes the same, despite the different shapes and volumes. The reason the water levels equalize is due to hydrostatic pressure. At any given height, specifically at the bottom, the pressure depends solely on the height of the liquid column. This means that the shape or volume of the vessel does not influence the pressure at a specific depth. So we can say here hydrostatic pressure is determined by the height of the liquid column, not the shape or volume of the container. So it depends only on the height of the column. Now we are going to explore atmospheric pressure measurement principles and gauge pressure calculations. So atmospheric concept. At any given point, all right, the pressure of the atmosphere equals to the weight of this column of air. This is why atmospheric pressure decreases as we go higher in altitude, where the column of air is shorter. At sea level, this pressure is standardized at 1 atmosphere. Alright, and we know 1 atmosphere is equal to 1.103 into 10 raised to the power 5 pascals. So, at sea level, the atmospheric pressure is approximately Pa equal to 1.013 into 10 raised to the power 5, and Pa, or we can say Pa equal to 1 atm, which is equal to equivalent to 1 atm. Historical development. So Here, Torricelli, an Italian physicist and mathematician, was the first to measure atmospheric pressure. All right. So Torricelli 1608 to 1647. Here, observing the height of the mercury in a tube, he could determine the atmospheric pressure. Now, let's start by introducing Torricelli's mercury barometer. This device is a fundamental in measuring atmospheric pressure. Notice how it's simple and ingenious tool that uses mercury to provide accurate pressure readings. Here we have a long glass tube closed at one end and filled with mercury, which is then inverted into a trough of mercury. This setup creates a vacuum at the top of the tube, allowing us to measure atmospheric pressure. The figure 9.5a shows how the mercury level in the tube changes with atmospheric pressure. So look at figure. There are 2 points A and B, and the height is h. So the device is known as mercury barometer. It's a classic example of how simple principles can lead to significant scientific advancements. Now, let's start by looking at the mercury barometer, which is a device used to measure atmospheric pressure. Notice the figure of the mercury barometer in figure 9.5a. This instrument uses a column of mercury to determine pressure exerted by the atmosphere. So, in the mercury barometer, the space above the mercury column contains only mercury vapor, which exerts negligible pressure. This is important because it allows us to assume that the pressure at the top of the column is effectively zero. As a result, the pressure at point A, which is at the top of the mercury column, is zero. Now let's consider the pressure inside a column at point B. This pressure must be equal to the atmospheric pressure at point C. Look at the figure outside the column. So this equality is what allows the barometer to measure atmospheric pressure accurately. The atmospheric pressure denoted as PA is given by the equation, that is PA equal to rho GH. This equation is very important. Here rho represents the density of mercury, G is the acceleration due to gravity, and H is the height of the mercury column. So in this equation, rho is the density of the mercury, which is a constant value. So H is the height of the mercury column in the tube. This height changes with atmospheric pressure, allowing us to measure it. Let's see same standard values now. So first standard value, height of a mercury column at sea level, which is approximately 76 centimeter. Alright, mercury column height at sea level 76 centimeter. And 1 torr is equal to 1 mmsg, which is equal to 133 pascals. Alright, so this is the relationship between torr and mercury and pascal. Now, by introducing the open tube manometer, this is a fundamental instrument used to measure pressure deficiencies. Alright, so the open tube manometer is particularly useful because it provides a simple a simple effective way to measure pressure differences. Imagine it as a U-shaped tube particularly filled with liquid, where one end is open to the atmosphere. The pressure difference causes the liquid to move, and this movement is what we measure to determine the pressure. So here we have an figure 9.5a open tube manometer. Let's take a moment to observe the structure and how the liquid levels differ in the two arms of the tube. Now, open tube manometer. Uh, the U-tube manometer contains a suitable liquid. For measuring small pressure differences, we use a low density liquid like oil. This is because it allows for more precise measurements without requiring large volumes of liquid. So, for larger pressure differences at a high density, liquid such as mercury is used. Mercury's high density means that even small changes in pressure results in noticeable changes in the liquid's height, making it ideal for these measurements. So now gauge pressure. Gauge pressure is the pressure relative to atmospheric pressure. So the formula for gauge pressure is gauge pressure is equal to absolute pressure minus atmospheric pressure. This equation shows us that gauge pressure is essentially the difference between the total pressure and the pressure exerted by the atmosphere. So we can express gauge pressure mathematically. P gauge is equal to P minus PA is equal to rho GH. Here P is the absolute pressure, PA is the atmospheric pressure, rho is the density of the liquid, and G is the acceleration due to gravity, and H is the height of the liquid column. This formula helps us calculate the gauge pressure. Example 9.3. The density of the atmosphere at sea level is 1.29 kg per meter cube. Assume that it does not change with altitude. How high would the atmosphere extend? Let's solve this question. So let's look at the information we have. Begin by listing listing the given data. So first we have the atmospheric density, which is given as 1.29 kg per meter cube. Atmospheric pressure 1.01 into 10 raised to the power 5 Pascal. Acceleration due to gravity 9.8 meter per second square. Atmospheric pressure PA equal to rho GH. Alright. So for formula can be rearranged to solve for H. So the rearranged formula is H equal to PA divided by rho G. So by substituting the values, and you will be get the H. Now let's solve for the height of the atmosphere. We will use the formula for pressure in fluid column, which relates pressure, density and height. So H is equal to PA divided by rho G. So substituting the known values into the formula, we have 1.01 into 10 raised to the power 5 divided by 1.29 into 9.8. So simplifying further, we get H is equal to 1.01 into 10 raised to the power 5 divided by 12.642. So simplifying further, we get H is equal to 7989 meter. Alright. Or we know 1 kilometer equal to 1000 meter. So it will be 8 kilometer approximately. Therefore, atmosphere would extend approximately 8 kilometer if density remained constant. Reality check. In reality, atmospheric density decreases with height, and the atmosphere extends over 100 km with decreasing pressure. So weather changes often correlate with mercury level drops of 10 mm or more. Let's now summarize what we have learned in this lecture. So pressure variation with depth. In a fluid at rest, the pressure difference between 2 points is given by P2 minus P1 is equal to rho GH. The absolute pressure at the depth is P is equal to PA plus rho GH. And hydrostatic paradox. This is very important. Connected vessels containing the same fluid will have identical liquid levels regardless of their shapes, demonstrating that pressure depends only on depth, not on the container shape. Atmospheric pressure. At sea level, atmospheric pressure is Pa equal to 1.013 into 10 raised to the power 5 and Pa equal to 1 atm. Torricelli's mercury barometer demonstrate this through the relationship Pa equal to rho GH, where H is the mercury column height. Gauge versus absolute pressure. Gauge pressure is the difference between absolute pressure and atmospheric pressure. Mathematically, it will be P gauge equal to P minus Pa equal to rho GH. This is commonly measured using manometers. Pressure measurement. Instruments like mercury barometer for atmospheric pressure and manometers for pressure differences utilize the principle of hydrostatic pressure. Standard atmospheric pressure supports a mercury column of approximately 76 centimeter height. We have 5 practice questions. So first, a swimming pool is 2 meter deep. Calculate the pressure difference between the surface and bottom of the pool. The gauge pressure at the bottom of a container filled with oil is 2000 Pascal. If the density of oil is 800 kg per meter cube and G equal to 9.8 meter per second square, find the height of the oil in the container. At a certain location, a mercury barometer reads 74 centimeter. What is the atmospheric pressure at this location in pascals? Two connected vessels contain water if the pressure at point A is 15,000 Pascal and point B is 0.5 meter below point A. What is the pressure at point B? And last, pressure goes at the bottom of tank reads 30,000 Pascal if atmospheric pressure is 1325 Pascal. Alright. What is the absolute pressure at the bottom of the tank? So these are the practice questions and these are homework for you. Alright. Thank you for your attention. I hope these lessons are helpful.